Good morning. Good morning, friends. Glad to be with you this morning in Calvary's Great Hall for our formation class. And for those of you who are joining us online, glad to welcome you into this community as well. This is the third in our series of Faith at Work. We've been asking folks to reflect on how their spiritual journeys intersect with their career paths, and however they would then respond and answer to that prompt. And we've had some great conversations so far with Kat Gordon and Annie Nix, and delighted to welcome someone who maybe doesn't need quite as much of an introduction or welcome, but is our friend Dave Rupke, parishioner here at Calvary. Just to tell you a little bit, though, that Dave, of course, is a professor at Rhodes College in the overlapping Venn diagram circle of physics and astronomy. And I am particularly excited about today when I get, a little overwhelmed and need a perspective check. My tendency is to think about whale migrations and bird migrations as a way of expanding the bigger picture. And I know that today that picture is going to expand even more because we're going to be talking about galactic wind or galaxy evolution or something, I don't even know. And maybe a few pictures from the Webb Telescope, which is just perhaps a personal favor to me because I'm so excited and entranced by the images that are coming to us from the Webb Telescope. So those are the things that I was kind of wondering about. I have no idea what Dave's going to talk about, and I'm excited to hear. So we're really glad that you're here with us this morning to share a little bit of your perspective. Come on up.
Thanks, Catherine. That was a generous introduction. I'm happy to be back up here with you all. I think the last time I got an opportunity to speak in Sunday school, I was an emergency fill-in. My wife Heidi was helping out with organizing Sunday school a year ago before Catherine came, and somebody canceled at the last minute, and so on Friday or Saturday she said, or maybe I volunteered. I can't even remember, but anyway, I ended up here with pulled something out of the vapor. It was something I'd done previously. But this morning, I'm happy that I had some more time to prepare and talk to you about some things. First, I want to say I've been really inspired by the last couple weeks. And I see Kat's here this morning, and Kat Gordon and Andy Nix from last week were just really great. And I feel like I've learned a lot. And one thing that struck me about those two presentations was they were talking about transitions and how that was important in their sort of journey. And so it made me think a little bit about what, my own journey, as Catherine said, this is ostensibly, how our work lives intersect with our faith. And so I was thinking about how I saw that. And so I'll start with just a couple of ways that I've seen that happen for myself. So I was listening to, I'm not just trying to get brownie points here by showing poetry, because I know Scott and Catherine love poetry. But okay, good. This is a poem that I heard on Padre Gotuma's Poetry Unbound podcast. I think it's the beginning of season 6 or something. And I was listening to it, and of course it was a great poem, but I was struck by, a lot of things in the poem, but these two lines in particular in the context of what I'm going to talk about this morning. So I'll read them. No two trees are the same to raven, no two branches are the same to wren. And so my version of that is no two galaxies are the same to astronomer. And the reason I bring this up is because, I've always been interested in science. I really loved science as a kid. And I would pull out my dad's backyard telescope and, look at the moons of Jupiter, and that was very exciting. And I was in graduate school thinking I was going to do, some other physics thing. And then I took a course on galaxies. And I didn't have to take this course. I just was kind of interested in it. And I was learning about, I was seeing pictures of galaxies, and I was learning about all of the sort of beautiful physical puzzle that a galaxy can be. I like to think of it a little bit like a biological organism. There's so much complexity there. And so to me, like seeing pictures of individual galaxies was a real, that was a moment where I, saw that this is something that I would really love to explore more and like to understand why this galaxy is different from this one. And what's behind that? So I am a scientist. I do come at it from a physicist's perspective, and so I think about the equations and the physical laws. Sort of the why of why these things look like they do. So I'm inspired by the artistry, but also I nerd out about the why. What's really going on behind that. So I guess in that spirit, then I'll show you. I'll show you the first image here. And when Catherine asked me to do this, it was pretty clear that I needed to show some pictures from the James Webb Space Telescope. No, and that's okay. I mean, I'm excited about all the amazing discoveries that are enabled by the beautiful, or the amazing instruments and telescopes and things that we're putting up and building. And this one in particular is this new telescope that NASA launched about a year ago, is one that I'm excited about too. So it's like all of the observatories that NASA has launched. It was a long time, it took a long time in gestation, and this one cost a lot of money too, although actually not much more than the last sort of great observatory of its kind. And I know I was excited about it because, I got up on Christmas morning and watched the launch at 6 or 7 a.m., I think, with my son. So, I was ready to do that. That was my Christmas present, I guess, was seeing it launch and work. And I guess I've been fortunate as well to be able to participate in some of the science that James Webb is doing. And so, I'm excited about the science that I'll show you here, and I'll talk about some of the science that I'm doing in relation to that. But also that I think it's a gift to all of us that we can enjoy these amazing discoveries. So I'm excited to talk about that stuff with you. And actually some of it I learned about while I was preparing for this. So that was exciting for me. So this image is an image of a galaxy. It's called M74, which is just a label. We give galaxies labels. Sometimes we give them fun names, but usually it's just a label that comes from a catalog. This particular catalog was crafted by a Frenchman named Charles Messier back in the 1700s. And he cataloged a little over 100 galaxies and nebulae and other things. And he was one of the first people to sort of make a catalog of these very diffuse things that look like clouds. They called them nebulae, which is Latin for cloud. But of course, now we know that some of them are these enormous galaxies. And this particular image is an image of the center of a galaxy. It's a spiral galaxy, as you can see. It looks kind of like a pinwheel. And I mean, if you just look at the image itself, it is kind of a work of art. And I will say that the folks who make these images, are highly trained, folks who do this all the time for a living. And, when I make an image for I sometimes have to make images for a paper, say for a scientific paper. I can't do this kind of thing. There are folks who are really good at this. So it is kind of a work of art, I would say, in that sense, not just in the thing itself, but also in the process by which this image is made. So, I think I look at an image like this, and it's a little bit like looking at a work of art that you would find in a museum. I also get excited about the science that underlies it. And what's exciting about this particular image in comparison to, say, what we might have seen before is, I can show you on the next slide, it's a comparison. And it's a little, from where you're sitting, it may be hard to see all the details. So I'd encourage you to go to, once we're done here, you can go to jwst.nasa.gov and, search to your heart's content, and there's a lot of amazing stuff there. On your left, you'll see an image from sort of what was NASA's previous premier observatory, the Hubble Space Telescope, and was launched about 30 years ago and has been, producing amazing and stunning science and imagery, visual imagery that all of us can relate to. And I think it's transformed astronomy, but it's also transformed the relationship of people to the work of astronomy, because it's made sort of the wonders of the cosmos very accessible. And so I think that was revolutionary. And so that's the image you'll see on the left is from that telescope. The image on the right is from our new telescope, the James Webb Space Telescope. And what's different about that? Well, it's bigger. And when I say bigger, I mean the size of the mirror is bigger. And if you think of a telescope as a light bucket, you want to collect as much, collect as many. I think of light, physicists think of light not just as, a stream of stuff that we see, but as individual particles. So that's one thing that we learned in the 20th century, is that light is actually, you can think of it as being composed of little particles. So if you think of these little raindrops of light coming down to us from the cosmos, and we're collecting them in this big light bucket. And so the bigger the light bucket we have, the more of those light particles or photons that we can collect. So we collect a lot of those, and then the more that we could collect, the fainter things we can see. The other two things that are revolutionary about this telescope are that it's, because of that size, it can also see things in much greater detail. So it turns out that the detail with which you can see something is indirectly, in physicists speak, we would say it's indirectly proportional to the size of the mirror. So what that means is that, in simpler language, that as the mirror gets bigger, your ability to see things gets better, and the size of the thing that you can see gets smaller. So we can see much finer details with a bigger mirror. And that turns out to be important in this case, because the other thing that Webb is doing is it's looking at longer wavelengths. So if you look around at each other, you can see each other because, well, maybe I'll ask this question. Why can you see each other? So raise your hand if you think you might know the answer to this. Yes. That's right. So Michael. Yeah. That's right. So as Michael pointed out, we see because we have receptors in our eyes to perceive the light. So let me ask the question a little differently. How the light that's coming to us, where does it come from? Can someone else answer that question for us? If not, I'll answer. I don't want to put people on the spot here, but you're welcome to, as I tell my students, it's okay to answer it and be wrong. I'm not asking this question, just expecting everybody to have the right answer. Any guesses? Oh, yes, Laren in the back there, way in the back. Yes, it bounces off you. It's reflection, and I heard reflection here. Yeah, so light is coming from the light bulbs up there and reflecting off you, and then you're perceiving it with your eyes. It turns out that we also emit light, and that light that we emit is due to our temperature. So what's the temperature of a human? 98.6, okay, yeah. It's, I'm not a biologist, so I'll just leave it at that. That's what I learned too, 98.6 Fahrenheit. So because of that temperature, you emit light, and the term that physicists use for the kind of light that people emit is called blackbody radiation. And anything that has a temperature, that can be, that you can look at that and say, oh, that's, 50 degrees. then that's emitting light, emitting black body radiation because of that temperature. And for humans, we emit at infrared wavelengths, and so wavelengths that the human eye cannot see. But, when you've heard of night vision goggles, right? So when people do that, what you're seeing is you're seeing the emission from people. So going out in space now, right? Everything in space, well, a lot of things have a temperature, can be characterized by a temperature. But the temperatures you see in space span a huge range, all the way from 10 degrees. And when I say 10 degrees, I mean, I use a different scale. Astronomers use a scale called Kelvin. And the coldest something can be is 0 Kelvin. And when something is 0 Kelvin, everything stops. And so nothing can actually be that cold. 10 Kelvin is really, really cold. All the way up to millions or tens of millions of Kelvin. And that's, you see temperatures like that at the center of the sun or, other dramatic places. So everything in the cosmos, many things have a temperature. And the things that we want to look at in the infrared that have a temperature, they have a temperature sort of in the range of 10 to 100 to maybe 1,000 Kelvin. And what you're seeing in this galaxy on the right, so how many of you have seen the Milky Way from a dark site? Okay, I see a lot of hands. So what you see there is brightness, right? You see things that are brighter, but you also see a lot of splotches in there. So it turns out that if you could see the Milky Way, if you could see the Milky Way in all its glory, then it would be extremely bright in the sky. But your view is getting blocked by cosmic dust. And when I say dust, it's not, actually one of my kids' chores yesterday was supposed to be dusting. I think he forgot, but there was a lot of other stuff going on. So the dust in space is just sort of debris. It's stuff that, most of the cosmos is made of very simple, the simplest chemical elements, but it also, all the other elements are contained in, out there in the cosmos. And dust is a lot of carbon and silicon, so a lot of the most common elements in the universe. And this dust blocks visible light, so it keeps us from seeing a lot of the cosmos. So by looking in the infrared, we get two things. One, we can see that dust emitting light, so we can see that dust glow. And then it turns out we can also see through the dust by looking in the infrared. So we get a twofer. And so on the right, on the left, if you look at all those brown splotches in the galaxy, that's the dust blocking the starlight. But then if you compare to the image on your right, so you'll see that the dust, and maybe you, again, hopefully you can see that, is that it's glowing. So that dust is now glowing in the infrared. And then we can also see things there that we couldn't see before. So you can't see it as well in this image, but you can see things through that dust that you couldn't see before. And then the image in the center is sort of a combination of those two, using fun colors and, just to show that those two things are complementary.
You mentioned the mirror. How big is the mirror?
The mirror size of the James Webb Space Telescope is about 6.5 meters. So I'm 2 meters tall, and so 3 of me stacked up. So maybe the height of this, not quite the height of this room, but getting there. Yeah. And putting a big mirror in space is really hard. They had to fold it up, and that was an amazing engineering challenge. I will say it, and this is. Gets to I suppose speaks to we have community at church. The nature of science is a really community endeavor, and all the folks who worked to put this telescope in space and all the work that went into that is pretty astounding. So that's one part of it that really amazes me. So, okay, so now we'll bring in the other aspect that I was going to that connects to our faith. So this is one of my favorite parts of church is when we do Eucharistic Prayer C. So I was really excited this summer when we did a bunch of Eucharistic Prayer C. So we're going to say this together, and then I'll talk about it for a minute, and then I'm going to show you some more images. Lift up, okay, you get to do the italicized part, of course, you know what to do. Lift up your hearts. Let us give thanks to the Lord our God. It is right to give God thanks and praise. God of all power, ruler of the universe, you are worthy of glory and praise. Glory to you forever and ever. At your command, all things came to be, the vast expanse of interstellar space, galaxies, suns, the planets in their courses, and this fragile earth, our island home. From the primal elements, you brought forth the human race and blessed us with memory, reason, and skill. You made us the rulers of creation, but we turned against you and betrayed your trust, and we turned against one another. So you can guess why I might get excited about Eucharistic Prayer C. I actually heard this first when my wife and I came to the Episcopal Church when we were living in Hawaii. And so this is, and they actually did Eucharistic Prayer C all the time there, I think. So, and maybe the reason is when I heard this, I was like, you know, this fragile earth, our island home, I was like, oh, this is the special Hawaii prayer, because we say this from the island. And then I came to Memphis and we said it, and I was like, okay, maybe I was wrong about that. I'll chalk that up to my, novice Episcopalianism. But yeah, even now when we say this prayer, it just connects with me at a really deep level, and I'm grateful for the times when we do use it. So I'm going to sort of take this prayer and just highlight a few things, and then show you some images connected with those things, and talk about how those things are cool and might speak to you. So first, the vast expanse of interstellar space, and galaxies and primal elements. So this kind of all connects very directly with the things that I do. So this is an image of one of the first deep images that the James Webb Space Telescope took. And this is an image that may look familiar for those of you who follow these sorts of things. The Hubble Space Telescope did something that was that actually I have always shown my students, and even not just in astronomy courses, I'll show them in other courses that I teach. It's called the Hubble Deep Field, where the Hubble Space Telescope stared at a region of space for days and days, took this really deep image of the cosmos. And the purpose of that is that, actually I was just grading exams yesterday where I asked my students, so, how do you explain the phrase that the further away we look, the farther back in time we look? And so the answer to that is that light takes time for us to reach us because the light moves at a particular speed. And so as we're looking further away, that light has taken a long time to get to us. And the further we look, the longer it's taken. So by looking at more distant objects, we can look at the universe as it was in the past. And we can look so far now that we can actually see the universe in its infancy. We can look almost back to, pretty far back. So one of the goals of this new telescope was to find the first galaxies. And one thing we've learned about the universe in, I would say, the last 30 years is that, so Immanuel Kant, he coined this term island universe for galaxies. It turns out that galaxies are not islands, that they're, at sea amid a huge ocean of stuff. And that stuff is really hard to see, but when we go and look for it and look really hard, it's there. And that's part of the science that I'm interested in, actually, is how galaxies are connected with their environments. But what we're seeing here is just a sea of galaxies. We're not actually seeing all that stuff in between, which astronomers call the cosmic web. But these galaxies, we're seeing them, as they were, in some cases, a few 100 million years after the universe was born. And we're talking about a universe that is 14 billion years old. So we are now finally starting to see some of the first galaxies. And this is just one of the very first images from Webb. So you can imagine what else is to come. This next slide is kind of zooms in onto that. And this is one of these press release images, so it's got some, fancy lettering and things like that. But what I want you to pay attention to is the fact that there are some little boxes scattered throughout the image, and those little boxes are pointing to some bigger boxes there that show little smudges. And of course, because these things are really far away, they look like little smudges. We don't have a lot of spatial resolution, as an astronomer would say. We can't see things in much detail. But again, that's why with Webb we want to increase that level of detail. But also, the light bucket that I talked about makes it possible to actually see these things. And then finally, the most distant things, they get redder because of the expansion of the universe. And so that's the infrared part too. So all of these pieces combined together allow us to see some of these first galaxies in the universe. And then finally on the right are the spectra. And these spectra are created when we send the light through something like a prism. So Isaac Newton was the first, at least the first person we know of, to take a prism and spread out light into its component colors and realize that white light is made of a whole bunch of different colors. So you spread it out and then he actually put it back together into white light. So we can do that now with great detail and see a lot of what's going on in galaxies by looking at spectra. And so this is a lot of the science that I do, is I get to kind of peel these, kind of unroll the light from these galaxies and look at all these details. And that's where a lot of the physics happens. And so where we can learn about the gas in these galaxies and the dust and the motions of these things and the composition and all of the other interesting things that are going on. And so the Hubble Space Telescope was revolutionary because of its imaging capability. So producing these amazing images. So, at some level, that image I showed you earlier with the Hubble Space Telescope image and then the James Webb Space Telescope image, and you're like, yeah, that's amazing, but they don't look all that different, right? So Webb is producing, new views, new images. But from my point of view, what Webb will be really revolutionary for, I think some of that imaging capability as well, and some of the, ability to stare at the things that are furthest away, is its ability to produce these amazing spectra. So spectra like this are things that, I'm used to seeing from the instruments that I use on the ground. And so to see them produced by this telescope, I was just astonished. So I'm really excited about these spectra. And what you're seeing there is highlighted. You can't see the words, but what's highlighted are some of the basic chemical elements in the universe. So hydrogen, oxygen, and so we're seeing these elements, as far away as we possibly can in the universe. And so that's, these primal elements that were produced in the first stars in the universe. So this is just after the universe was born, assuming that the Big Bang is the birth of the universe. We could have a discussion about that too, but that's our current model for the universe, is that the universe was born, at this time we call the Big Bang. And very shortly after that, the first stars formed, and the stars are sort of the furnace for the chemical elements that we are all made of. Most of the universe is the lightest chemical elements of hydrogen and helium, but we're all made of other things. We've got a lot of hydrogen too, but we also have carbon, nitrogen, oxygen, iron in our blood, you name it, right? So all of those elements have already appeared, in very early in the universe, and now we're seeing them for the first time. So the oxygen that you breathe, we're seeing it there in these galaxies. So looking at a few more galaxies, I like looking at galaxies, so I'll show you a few more. And it's, the Webb has already produced some pretty spectacular images of galaxies. And I'll talk a little bit about what we can learn about galaxies by studying these. This is a collection of galaxies that was named. There aren't, often, you'll find that the folks who catalog these galaxies, they get their names attached to them. That's not so true anymore because now we do big surveys and it's not just one person doing this, right? But in this case, some guy named Stefan, I guess, so found this collection of galaxies. So it's called Stefan's Quintet. And it's kind of unusual to see 5 galaxies together in this close proximity. And in fact, one of those is just a chance proximity, so it's not actually physically proximate to the other 4. But the other 4 are related to each other, and they're a little group of galaxies. The Milky Way that we live in is actually part of a group of galaxies we call the local group. And so this is its own little group of galaxies, these 4 galaxies. And there's a few things that we can learn from this quintet. And one is kind of a reminder that galaxies are interacting with each other, that they're not just these island universes, that they do, mostly via the force of gravity. They touch each other, they brush by each other and change each other. And sometimes they actually violently crash into each other and make a whole new galaxy. Of course, these processes happen over billions, hundreds of millions, billions of years. So, it's not, from a human perspective, it's not very dramatic. But we can make simulations on our computers of what this process might look like, and then we can speed things up a little. But another thing that's so this is a Webb plus Hubble image, I think, again, and this is actually when I was a postdoc at Hawaii doing some research there. I got to take some spectra of some of these. Some of the star regions that are forming stars in these galaxies, because we were looking at how much of the chemical elements were in these different parts of the galaxies and how that interaction process affected how these heavy elements were distributed in the galaxies. So this is just Webb's view, and I love this. I love the color and sort of what I love about this image is how it shows the sort of complex structure of what we're seeing here mainly is the dust and gas in these 5 galaxies. And it really is beautiful to see these images. And what's cool behind that is that, all of the physics that are creating these structures. And I'll be honest, I'm not an expert on all of that. But some of the stuff that I do study relates to, if you look at the galaxies on the right, so it turns out the galaxy on the left is the interloper. It just happens to be in the field of view. It's photobombing, I guess, is what we would say now. So the real action is happening on the right, and so those galaxies, the gas and dust in those galaxies is very chaotically distributed, as you can see. And it's not in the nice regular pattern that you see on the left. So the galaxy on the left is just the gas and dust are just kind of going around the galaxy, ho-hum, minding their own business. And on the right, everything's been kind of, gone to pieces or, thrown out. And what's happening is that the gas is, the gas is hitting other gas. And so that makes some of the gas light up. And so, for instance, the kind of greenish ridge you see on the right there is due to that shocking process where the gas is from one galaxy is hitting the gas from another galaxy. And so that's a common feature of these galaxy mergers. Another thing that's cool is that, and this relates more directly to the kind of research that I'm doing with some of the data we're getting from the James Webb Space Telescope. So the galaxy on the upper part of the image has a really bright point there in the center. And with Webb, you can see that. You see these bright points as these six-pointed, these sort of, typically when you see something bright in an astronomical image, it'll have these spikes coming out. And that's just an effect of, it's not an actual characteristic of the thing itself. It relates to how the light is collected. And Webb, because of its 6-sided mirrors, it has these hexagonal mirrors, which are kind of unusual. It produces these spikes that are 6-fold, right? And so in this sort of hexagonal pattern. So you can just barely see that in the upper right. And actually there's another bar that goes across that's due to some other effects. So it's like an 8-pointed star, I don't know. But what that's saying is that there's something really bright there. And when you see something really bright at the center of a galaxy, it's often because some of that gas has gotten down to the center of the galaxy. And one amazing thing that we've learned in the last decades is that most galaxies have just at their very center a black hole. And the black holes at the centers of these galaxies are very, very massive. So, it might be 1 million or 1 billion times the mass of the sun. Now, it's still just a very small fraction of the total mass of the galaxy itself. So in terms of, its gravitational effect, you're not going to know it's there unless you, go and get right next to it. So you're a known danger from the black hole at the center of the Milky Way. This beast at the center of the Milky Way. But because of the power of gravitational energy, and because these things are so massive, when you get gas down into the center there, it lights up. It gets really hot. And remember, I told you that things that have a temperature emit radiation. And so this really hot stuff lights up. And paradoxically, black holes are some of the brightest objects in the universe. So we can see these supermassive black holes lighting up, sort of beacons across the cosmos. So this particular galaxy has something that's really bright in its center, and that's telling us that there's a supermassive black hole that's secreting gas and is lit up and is emitting light. And what we have learned over the last 10 to 15 years is that those black holes can affect the evolution of their hosts. So it turns out that those two things, the black hole and the galaxy itself, are connected, that they evolve together, and that part of the reason for that may be that the black hole itself kind of like feeds back on its host, and it's sort of, it's pulling in the gas, and then it pushes back a little bit. It says, whoa, hold on there. And so when the black hole lights up, right, it also, a lot of energy is being emitted. And that energy then connects with the gas that's trying to get in, and it pushes it back out, and that can cut off the accretion. And so there's this kind of back and forth process that we call feedback. So, like when I'm using this microphone, if I point it at the speaker and you start hearing that huge squeal, that's a negative feedback, right? Or excuse me, that's a positive feedback. So it's sort of amplifying the signal. The negative feedback in galaxies is trying to say, let's slow down the black hole accretion, let's slow down the star formation a little bit, let's regulate things. And so there's these really cool processes, a little bit like the biological processes that we have to regulate our temperature or the sugar content of our blood or things like that. And so one of the tools that Webb has is the ability to take a spectrum at a whole bunch of different locations in this galaxy. And by doing this, we can study those feedback processes that I was talking about in great detail. So this is just an example. The galaxy that I was talking about, that galaxy on the upper part of the image, now we're sort of zooming in, and we're taking an image in several different wavelengths of light. So this, when I talked about a spectrum spreading out the colors of light, and so we look at very particular colors or wavelengths, and we can learn sort of about the physics of what's going on. And so we can look at different chemical elements, for instance. So the images you see on the bottom are images of that black hole feeding back onto its host galaxy in the light of iron and hydrogen and different forms of hydrogen there. So iron is the one that's the second, not the leftmost one, but the next one. The other ones are actually all hydrogen, but one is atomic hydrogen, so hydrogen, just one hydrogen atom. The other is molecular hydrogen, which is two hydrogen atoms put together. And so that actually gives us a different picture of this. There's a whole bunch of other chemical elements in there too, but those tell us something about what's going on. The molecular hydrogen is part of the stuff that's feeding into the black hole, and then the other things are part of the stuff that's being pushed out, so the feedback. So there's the feeding in, and then there's the feedback. And so, just this past week, I was taking data cubes like this. So this is what we call this image, when we get an image of a whole bunch of different colors. And, what astronomers do is we take this data, actually we don't actually go up to the telescope to do that. Everything gets programmed in, the data gets taken, and then you get an email that says, you've got mail, you've got data. And so I go somewhere into the ether and download that data to my computer. And what we've been doing is preparing all of our software. So a lot of what I actually do is writing software and working with collaborators to figure out once we apply that software, what do we do? How do we interpret that scientifically? So it's a multi-step process of doing that. The past week I've been working on some data cubes like this with our software and trying to work on our software a little bit. Got a few bugs, but also having scientific conversations. So the team that I'm on, when you want to use a telescope like this, just like if you need grant money for a nonprofit, or you want to do a capital campaign, and you kind of need to plan it and make a really good proposal. You've got to convince people that this is worth doing. So the same thing when you want to use a telescope like this. There's a lot of competition, so you have to write a good proposal. And so I was fortunate that some other folks who wrote a really good proposal pulled me in and said, hey, we want to use your software and let's connect you with this program. And this particular proposal call was to use some of the first data from the telescope, but then also produce something that would be useful for the scientific community. So that's what I've been working on with this collaboration for the last couple of years, including Rhodes undergraduate students, so folks from where I work. And so anyway, that's our first sort of results from this are going to be released pretty soon. And the paper is kind of in the works, and supposedly there's going to be a press release. That's what I hear. But somebody else is handling that. So if it doesn't happen, but I'm pretty sure. I will say our images are not quite as beautiful as the ones that you see from those first press release images. Because these data cubes are much more complex, you get a lot smaller field of view, we call it, and so the details are, it's all in the spectra, so you have to kind of trust us that it's cool. All right, a few last things. I'm kind of running out of time, but I think it's worth bringing it down to where we are too, right? So this is all kind of out there, but stuff that we can learn about, and that's what's so exciting is that. That's part of what has excited me about studying galaxies is there are these, amazing, massive, complex structures somewhere out there, but that we can somehow bring them, here and learn about them and sort of all their glory, and that's really a great thing. So coming to the planets and primal elements, another thing that Webb is going to be able to do is teach us about the exoplanets in our galaxy. And when I say exoplanets, I basically mean all of the other planets in our galaxy, which are billions. So this is, to me, one of the most amazing things that we've learned in the last 20, 30 years, is that our galaxy is teeming with planets. So we, before 1990, we knew about, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, but then not Pluto, but there's a lot of stuff out there. And we've found a lot of new stuff in our own solar system too, little round things that are very far out and something called the Kuiper Belt. But now we know that there are planets everywhere in our galaxy. And probably every star has some sort of planet, probably a family of planets. And I'm just astounded by this. And I think, it's... to learn this, I think, tells us a lot about, sort of our place in the cosmos. I don't know exactly what that is, but I think it tells us something. And the one thing that Webb is going to do, and so, now that we've found these planets, and we're still just scratching the surface in terms of the number that we've actually seen, because they're hard to find, but then we can sort of extrapolate, throughout the galaxy. And now we can try to study these planets. So what's in them? What are they made of? And of course, one of the things we want to look for is signatures of life. And so people look for things called biosignatures. Most recently, I was learning about technosignatures. So, what might we look for if we were looking for intelligent life? Of course, that sort of search has been around for a long time, but I think it's entering a new phase. So I would say it's, likely that within certainly the lifetime of our children that, we will be able to answer the question of, how common is, some form of life in our galaxy. Intelligent life is a whole other question, but, I think we're going to start to be able to see some sort of, we'll at least have the chance to see signs of life on other planets. We'll see. Yes, Michael?
Will Elon Musk become the czar of Mars?
I hope not. Although I'm excited about, folks like that who get excited about these things and want to, well, that's a whole other issue and complex, and I shouldn't get into it probably. So a couple of, the first, again, this telescope is in its infancy and is, if all goes well, should be around for, and working and doing everything it should for 20 years. Knock on wood. But already it's seen in the atmospheres of some kind of unique planets, but still in planets, seeing water. And so this is a spectrum that is mostly just a bunch of wiggles, but what you're seeing there is actually signatures of water. So if you look through our atmosphere, you would see signs of water. And in fact, that's part of what produces our greenhouse effect, which keeps us nice and warm, although it's now making us a little too warm. So the water in our atmosphere is basically absorbs light in the infrared. And so that's what we're seeing in this exoplanet, is all those dips are dips from water absorbing light. And in this planet, we're seeing, this is kind of the spectrum upside down. So the hump that goes up is actually the planet absorbing carbon dioxide. So now we're seeing carbon dioxide for the first time in the atmosphere of a planet around another sun. So again, this carbon dioxide is a vital component of life. And going back to water, NASA's way of, their way of finding life in the universe has been to follow the water. So if we can find water, in particular liquid water, so atmospheric water doesn't tell us that life is there, but if we can find liquid water someday, that's a good place for life to exist. But carbon dioxide is at least something we need too, again, to keep us warm. Hopefully not too warm. We're working on that. All right. So, I'll just finish then by reminding us of, and kind of bringing us back to home, our fragile Earth, this fragile Earth, our island home. And actually just the other day I was showing my students this image of, does anybody know what, has anyone seen this image before? It's not Earthrise. That's a good guess though, that's another good one. So this is called, it has a name, it's called Pale Blue Dot. So that little, yes, sorry Raymond, I was showing it, I thought it was another image. This is the pale blue dot, sorry. But first I was showing you that, let me start with this one, thanks, sorry about that Raymond. This one is not called Earthrise, but it kind of looks like that. And actually you can see the Earth here and then up in the corner there is the moon. This is actually the first image ever taken of the Earth and the moon together, and it was taken by the Voyager 1 spacecraft in 1977, shortly after it was launched. So this is, I was alive in 1977. I wasn't capable of knowing about this then, but some of you may remember when, may have seen this image, who knows. But this is pretty remarkable that we can then step outside our island home and see it from afar. And then this one is the one that I thought I was showing you at first. This one is called Pale Blue Dot, and this one is taken in 1990 by Voyager 1, just before it was turned off and sent on its way into the into the vast expanse of interstellar space. And it looked back on the solar system and took this picture of the solar system, and this little pinprick of Earth just occupies a single pixel on the camera. So, it's this tiny dot, and, Voyager 1 at this point is beyond the orbit of Neptune. And this was, photograph was inspired by Carl Sagan, so he was on the Voyager team, and he really he suggested we take this picture. And so I think it's a good idea to remember sort of our fragility, and maybe, hopefully that will teach us humility as well. There is an effect, a psychological effect that astronauts experience when they go into space that's called the overview effect. And so many of them, when they come back to Earth, they have a different perspective on things. And so I think it's well worth our while to spend some time with images like this and to sort of try to help us develop that perspective. Okay, well, I'll kind of wrap up there with that, and I'm more than happy to take any questions if we have some time. Catherine's in charge here, so yeah.
You mentioned Carl Sagan. When I was growing up in the 70s, my dad and I watched Carl Sagan, watched Cosmos together. And from that moment, I had this fascination with things like that. I forced my kids to watch it, and the reboot with Neil deGrasse Tyson. And I just read this summer, it took me a very long time and I had to take notes, but Neil deGrasse Tyson wrote Astrophysics for People in a Hurry. It's a tiny little book, but it's very condensed, and for the layperson, it is fascinating. And for me, understanding that at whatever level has been a really interesting way for me to connect to my faith and to spirituality, because that connectedness of everything in the universe, that we're all made of interstellar dust. I don't know if that's a Carl Sagan or a Neil deGrasse Tyson thing, but to me that's really lovely, and it is connecting. And looking at those images and hearing you talk, it's like seeing the hand of God. I think it's just amazing. Thank you.
Yeah. Amen to that.
You said the Webb telescope is going to last about 20 years. Is there plans for some new and improved version for when that stops working?
Yeah, and first of all, I say 20 years. With a space observatory, you do your best, but you never exactly know what's going to happen. So that's why I was knocking on wood. It's in working with, first of all, getting it there and making sure it works when it gets there is an enormous challenge. And this one in particular was an amazing technological challenge, and I'm still kind of astonished that it works as well as it does. But you don't know what'll happen, and so I hope that it will last 20 years. That's currently what it can do if everything goes as planned. Yeah, astronomers, just like folks in other fields, are always thinking about what's next and what's the bigger and better thing we can do. And there's actually an official process for this something called the Decadal Survey. So every 10 years, astronomers get together and say, what do we want to focus on and what are our priorities? And that actually affects funding agencies. So, the National Science Foundation and NASA look at these recommendations carefully, Congress, and then try to follow those. And so it's going to be a while before we have something as big and expensive as this, but they're certainly already planning it. Yeah.
Michael.
Question. These other than NASA, private groups like the SUR, whatever his name is, and Elon Musk or SpaceX and whatever, are they improving the situation or making it worse?
Well, yeah, in my opinion, having more folks at the table and working on this is always a good thing. From a scientific perspective, I think that's great. And from the terms of, as an outsider, I don't know much about sort of the space, the rocket space industry, but certainly it seems like having private industry involved in launching things has been a really good thing, because they've been able to do a lot more cheaply and bring creative new ideas to the table. And so, from that perspective, I think it's healthy. But that's probably all I should say. And lest I overstep my authority or expertise.
So, David, I'm still thinking of your 4 or 5 galaxies, and the image that we see from deep space. You would assume that they're going to reorganize themselves into some significant thing that's closer together.
Right.
And I wonder if you could back out your view and not look quite so deep.
Yeah.
You could see that happen.
Yeah, well, so the way astronomers do that is we actually, so because these processes happen over such long periods of time, So to see things happen over time, what you do is you look at different distances. And so you can't look at the same galaxy, but you can look at things that might, say you look at this distance over here, and you could say, well, these things are maybe in the process of becoming these things that I can see a little closer here. And so you kind of have to do that sometimes on a more, sort of a statistical basis, and then you say, okay, let's look at this collection of things and we think maybe they, are the progenitors of these things that we can see over here. And that's part of what makes it challenging, is that, you can't watch things happen in real time, but you can try to say, okay, well, here's, based on what we know about the astrophysics, the properties of gravity and, how gas moves when it interacts with other gas, and how stars orbit each other, that you can sort of extrapolate. Does that help answer your question? Okay. Yeah.
Thank you, Dave. So you seem to be saying that your scientific work has given you a greater sense of humility, awe, and sort of wonder. And I'm wondering if you could talk a little bit more about that, and is that how science works? Is that sort of what science ought to teach us? Or I was just wondering if there's anything else you can say about that whole relationship.
Yeah. So I think for me that happens more on a subconscious level, and that it sort of it bleeds over into that's actually a tough question for me to answer, and I think in broad strokes, yes, but most of the ways I encounter these things are on a daily basis, in sort of very pedestrian ways. I wrote down, I think, Kat Gordon, when she was giving her Sunday school a couple weeks ago, referred to that phrase, ora et labora, and, I wrote that down and underlined it, and I was like, yeah, I've heard that before, but I was struck again that that's, the process of doing what we do on a daily basis is prayer and work, and that those things are intimately related. And maybe it's easy sometimes to look at science as sort of, being able to supply answers to things, but I think the scientific process is much more about exploring and trying to come to some understanding, but realizing it will never be anything close to the full reality of the universe. And so I think that maybe in my work, seeing the limitations of science, and that it's a very human endeavor, has helped me to remember that there are, that it gives us access to these things, but also that there are other ways of knowing the world. So which is a little bit of a strange answer to your question, I think, but maybe one that more is in accordance with my own experiences. Yeah.
Which is lovely. Thank you for sharing your own experiences and teaching us, but also inspiring us. This is just fantastic. And I'm sad that we have to stop and go to church. I'm not sad that we have to go to church, but I'm sad that we have to stop this conversation. Thank you so much for sharing your perspective, and a much larger perspective, as I was hoping. And a good segue that Kat will be back with us next Sunday as a bookend to our conversation about work and vocation and all the things that we might as we braid these threads together in our own particular lives and our own particular experiences. So I hope you'll be back next Sunday. Thank you again. Thanks.